Okay, we'll go ahead and get started. Tonight's Tech Talk is going to cover antenna analyzers. And we're going to focus primarily on analyzers that would be used for ham radio. There's uh, quite an assortment of antenna analyzers if you get into the commercial and industrial and military type applications. So we'll just stay focused on those for ham radio. And before we get started, I wanted to thank Tom, KC3IUB, who suggested this as a topic for one of our tech talks. So thanks a lot, Tom. So hopefully in this presentation, I can answer three questions that I think are relevant to antenna analyzers for a ham radio. First one would be just generally, what do antenna analyzers do? Second question would be, what kinds of antenna analyzers are there for ham radio applications? And the third question would be, why would I need one, or why would you need one? So hopefully we can come up with some answers for all three of those. The primary thing that an antenna analyzer does for ham radio is it gives you the ability to determine the resonant frequency of an antenna, so that you can adjust the antenna to get to the desired resonant frequency that you'd like to have. Now, if we take a look here at this schematic, what we're looking at is an antenna system which consists of the feed line and an antenna. And what we're wanting to know is, from looking at this point here, what is the standing wave ratio that we might expect. And this point here is important because this is where the either the external antenna tuner or the transceiver that may have an internal antenna tuner would be looking at the feed line. Now, if you get serious into really wanting to understand an antenna, you really need to do the testing at the antenna so you can remove the feed line effects. And then you could come back later and install different types of feed lines or model different types of feed lines to see what the feed line impact might be. So the antenna tuner has two basic functions. Not antenna tuner, the antenna analyzer. It'll have a some sort of variable frequency oscillator, and the purpose of that is to generate a fairly low power signal that would operate in the frequency range that the antenna system was designed to operate. And then it has to have some way of measuring the impedance at this point that it sees at that particular frequency. Remembering that impedance has two components, the resistive components, or the real component, and then the reactance components, either inductive or capacitive. And to illustrate that, we'll take a look here at a graph that you may remember, hopefully, from our general class studies, where we took a look at impedance as a function of frequency. And we'll start here with the capacitance reactance, capacitive reactance. And we know that at low frequencies, the capacitive reactance is high. Excuse me. And then as we increase the frequency, the capacitive reactance decreases and continues to decrease the higher the frequency we have. And then conversely, the inductive reactance starts at a very low level. Actually, at DC, or 0 hertz, the inductive reactance of an inductor is 0. And then as the frequency increases, the inductive reactance increases linearly, like we see here in the graph. So what we're wanting to do is understand, as the frequency increases, what does the combined reactance do on the antenna? And what we'll see, and what we have seen, is that when we get to this point where the inductive reactance equals the capacitive reactance, since one is positive and one's negative, they cancel each other out, and the only impedance left is the real part, or the resistance in the real resistance. And this is the point that we define as resonance, when both the capacitive and the inductive reactance cancel each other out, so there is no reactive component to the impedance. Now we take a look at this. We've been through this before, and maybe not in the same frame of reference that we're doing it now. When we were looking at the hextenna. The hextenna is the resonant dipole that we used at the POTA activation over at SB Elliott Park, and Judy uses it quite a bit on her POTA activations. And what it is, it's a dipole, a resonant dipole that is made up of two elements, and both elements are telescoping antenna elements that are connected at the midpoint and then tied to the feed line that goes back to the transceiver. So what this is a standing wave ratio plot. It's indicated over here in the corner, the SWR. And what we're doing is we're looking at the standing wave ratio of that antenna with the elements adjusted at 16 feet, 11.5 inches. And this was the recommended length provided by the manufacturer to begin operating. So if we take a look at this, as the frequency increases, we're going through the 20-meter band. As the frequency increases, the standing wave ratio decreases. We're down to about 2 here at 14 megahertz. This is where our lowest SWR is. And then as we increase the frequency, the SWR starts to go back up. So we ended up with a resonant frequency of about 14 megahertz, which is what is a fairly typical target that a lot of these antenna manufacturers look for, because this is the CW range of the band. In this case, since we're wanting to operate the transceiver in single sideband mode, we're targeting the middle of the general band for single sideband, and that would be 14.288 megahertz. So what we want to be able to do is figure out a way to move this point over to this frequency so we get our lowest SWR in the middle of the band that we want to operate. So what we did is we adjusted the length of the elements to 16 feet 9 inches, shortened it a little bit, and ran the antenna analyzer. And you see we shifted the resonant frequency to the right a little bit, a little higher frequency by making it shorter, but we're still short of the 14.288 megahertz. And then we made a final adjustment to 16 feet 4 inches, and we got our resonant point, the lowest point on the SWR curve, much closer to the 14.288 megahertz. So that's really the primary purpose of an antenna analyzer, is to give us the data that we need to make those types of adjustments. Now, the thing to note, I hear a lot of people say that their standing wave ratio is high and they want to bring it down. And I think that's a bit of a misnomer, because you're not really bringing it down. What you're doing is you're adjusting that resonant frequency to the point on the frequency spectrum that you want it to be, which it results in the VS or the SWR being lower. So it's not so much reducing the SWR, but moving that resonant frequency to a point that gives you the best standing wave ratio that you can get with that antenna. But what else can antenna analyzers do? A lot of things. Obviously, you can get the SWR. You can get the complex impedance and the vector impedance measurements, and this is all kind of in the weeds stuff. And just as a note, this list I got off of DX Engineering's website. They had a nice page set up on just general information on antenna analyzers. You can also get the return loss, which is a measure of the radiating effectiveness of the antenna, as well as the inductive reactance and capacitive reactance. You can determine the electrical length of a section of coax cable, depending on the model of analyzer. You can determine the feed line loss of the length of coax cable. Some of them can be frequency counters to measure frequency and generate signals that you may want to use for testing. A lot of them have the ability to graph the results with all the new digital stuff. Some have memory for storing graphs, and then you can take that information and download it, typically with a USB cable, to a computer for further analysis with software that's available, usually for free. And there's some multi-language display models. So all those things are additional things that you can do with an antenna analyzer. But the primary function that you'll probably use it for is in adjusting your antennas to move that resonant point of the antenna. Oh, and there's frequency range scanning in select models too. And then another way that the antenna analyzers are classified are by bands that they cover, where some are HF only, some are VHF and UHF. Then there's some units that are a combination of the three. The thing you want to be careful of when you select an antenna or analyzer is if you select one that's HF only, you're not going to be able to use it on your VHF and UHF FM radios that you might have in your car or in your base station or your HTs. So those are considerations you need to keep an eye out for when you go through your selection process. And this is just an example of various types of antenna analyzers you might see. There's a whole bunch of them that I would consider to be the I guess the equivalent of my commie radios. You can get all different kinds of them, but I think for ham radio, there are three manufacturers that I've seen that are kind of mainstays, I guess would be a good way to put it. One would be MFJ. Another one is Comet. They do a lot of antennas. Diamond may have some, but I haven't run across them. Didn't go looking for them specifically. And then RigExpert is another main manufacturer. There's another device that's available. I haven't used it, but I've seen, read some articles on them and a couple of YouTube videos, and that's it's called a nano vector network analyzer, VNA, and it does quite a bit of different things for electrically understanding networks. And one of the features of it is that it can be set up to generate standing wave ratio plots of antennas. The other thing that's kind of nice about this is that the price is relatively low compared to the other analyzers. I think I've seen them in the $50 to $60 range. They hook up to a computer. You can do further analysis on the computer when you download the data. Just the general sense I got of them, though, and this is just my opinion, there seems to be a little more technique involved, a little more uh, uh, adjustments and setting up in order to do what you want to do with it. But if you're willing to go through that learning curve to get familiar with the instrument, it can be a pretty good solution at a pretty good price. So it might be something you'd want to check out. There are a lot of different manufacturers I noticed that provide these things. And then this slide is also from DX Engineering. DX Engineering's website has a pretty good, it is a pretty good source for just general technical knowledge and a good way to look at what might be available. Excuse me. And what they did is they just put this comparison table up that shows the different types of antenna analyzers that they have available. And it's by no means an exhaustive list. There are a lot of other manufacturers as well, but this is the Comet. And let's go back. I don't know if I can go back a page without messing this up. But this analyzer here has a dual needle meter that you use to read the standing wave ratio and the impedance of your antenna. Then here's a line of MFJ analyzers, and they have a configuration where they have an SWR meter and either a power or an impedance meter that you can read as you adjust the frequency, and also a digital display that'll show you that same relevant information in digital format. You get into the RigExperts, they have a line of analyzers that are pretty capable in terms of being able to sweep a band and collect the information needed to generate a variety of plots, primarily standing wave ratio plots. And then they have this line here, which I believe is relatively new, but a smaller, more portable type of antenna analyzer. I get the impression it's intended primarily for field use. You could use them on a base station as well. It's just another capable line of analyzers that's packaged a little differently. Now the one I have is this one right here, the AA54, and I've had extremely good success with it. It's easy to use after you once get through a little bit of a learning curve, and it's worked quite well for me. So probably any of them on this table would do well for you. I don't believe the MFJs have the ability to store data that you can transmit. They may have units that do it, but typically with this type of a unit, you're reading the SWR at a certain frequency and then making a hand note of it and plotting by hand. And I could be wrong on that, but I'm pretty sure that's what you have to do with these types of analyzers. And then the question, why would I need one? Well, I guess to be completely honest with you, you really don't need one. You have some tools available. If you have a transceiver, whether it's a new one or a more vintage model, and what you can do is you can use, for example, this is the S meter off the Kenwood TS890S that I have. It's actually a digital display on the flat screen, but it looks like the old analog meter, the S meter, you see even on the older equipment. And you can see there's a scale for SWR, so you can set it up to display the SWR when you're transmitting. So that would be one way to get your SWR readings if you're wanting to adjust the antenna. The ICOM 7300 actually has an SWR graph capability in it, some other SWR tools and antenna tools that you can use. I didn't find it specifically, but I'm pretty sure the Yaesu FT991A is also similarly equipped. And you can also, in this case, is a base station meter that you would have connected between your radio and the antenna, and you can get your SWR readings off of that. Now I've got, oops. Okay, I may have to go back and do a little editing. This is a table that I made up for my analyzer. I do a lot of work with multi-band antennas, and what I wanted to do was to quickly be able to set up the analyzer so that I could test any or all of these bands quite easily. And the way my analyzer's set up, you can enter in a center frequency of the range that you want to cover. In this case, let's say 80 meters. The center range I've calculated for that is 3.75 megahertz with a sweep range of 1 megahertz. So that'll be plus or minus 500 kilohertz. And all I have to do is enter in that value, the sweep range, and it'll run through the frequency span, recording and plotting the SWR, and then I can note the resonant frequency on my pad here and see where we're at for any of these ranges. So what I'll do is I'll go through 80 through 10 meters, let's say, if I'm working on an 80-10 antenna, and then I'll also take a sweep of the full band where I go from 80 meters to 10 meters, and here's the center frequency I would set and the span. So that just makes it kind of handy. These are examples of screenshots off the AA54 that I have. Up here is just kind of the main menu. If I want to set the frequency, I hit the 2 button, and then I enter the frequency. And then when I set the range, I hit the 3 button, and I set the range. And then I can have it scan the SWR, and I can save it. I think the 6 button is what you use to save it. And then I can get a display up that shows the frequency that I'm at. I can set the frequency and read the SWR. It also gives you some information on the impedance. It has a screen that you can, at the frequency that you're at, it shows the SWR both numerically and in a graph. And then down here, if you're doing multiple SWRs on different bands, it'll show you the SWR in kind of a crude graph form here, which is handy if you're working on a multi-band antenna and are out in the field. And while you're scanning, and after the scan, it'll give you this graph of your SWR on the screen that shows you the SWR through the frequency range that you specified on the setup, and also more impedance information. So all that's pretty handy. If you're out in the field, you can also save the information of each scan to memory, and then you can download that into your computer with a USB cable. And then they have a free software package that you can use to generate some of the fancy graphs that we've looked at on the Hextenna, and we'll see a little later as well. So it's very capable analyzer. As I think when I bought it, it was kind of the mid range of their analyzers. I didn't need the color and some other features that they had. But I've since learned that this is discontinued, and it's replaced with an AA-55 zoom, I believe they call it, which gives you even more features, which includes color display. So you could probably still get this on eBay somewhere or something similar, but this isn't offered by the manufacturer any longer. And this is an example of the full graph you can get from the software after you download the data into the computer. What I have here is the 8010 infed half wave that's came from my antennas. This is the same antenna that we have at the clubhouse. And what happened was the element broke. I'd had it up in the air for a couple of years. The element broke, and I replaced the element with a heavier gauge element. And after I got it installed, I ran the full scan showing the SWR at 80 meters, 40 meters, 30 meters. There's 20, 17, 15, on down to 10. Gets kind of ragged towards the high end of 10 meters. And then it also shows, even though it's not specified, it's an 8010. I also wanted to check it at 6 meters. And you can see the SWR is pretty high here on 6 meters. And that's the reason why when we do the QSY to 6 meters on our Monday night nets, I'm not able to do that because I don't have an antenna with good enough capability to transmit on 6 meters. Now, what I did with this graph then is that when I installed this antenna initially, I did this same plot and saved it. And then after I did the replacement of the element, I was able to take this graph and compare it to the original graph that I did when it was installed new, and to determine that I was actually pretty much dead nuts on where I was when I put the thing up. So when you put up a new antenna and you get everything working, it's a good idea to make that kind of benchmark plot, and then you've always got something you can come back to reference if something happens at a later point in time. And then this is from the same study where I zoomed in to look at 80 meters. This is the standing wave ratio here on the left, the frequency on the right, 40 meters, 30 meters, and 20 meters. All that's looking pretty good. 17, 15, 12, and then 10. You see we're not too bad a shape down here, but then the SWR starts climbing as we go up in higher frequencies. And just kind of my rule of thumb that I use on my radios with the internal tuners is I figure if we can, I can operate pretty well below 3 SWR with the internal tuner. So if I get up over 3, then I'd prefer not to use it there. And this is the 6 meter result here. You can see we're at about maybe 4.8 or so through the whole band. So that's not too good. And that's about it. I think, again, I want to thank Tom for suggesting this topic. And if anybody has anything they'd like to get into, just let me know. We're always looking for topics for the tech talks at our meetings. So drop me an email, catch me on the air, or just let me know somehow, and we'll see what we can come up with. One thing wanted to note, this video I'm planning on putting up on YouTube with the other videos we have. So if you go to YouTube, you can search my call sign, K3SKS, and you should be able to find this and other Tech Talk videos. And our license study group videos are up there too, if you're into wanting to study for your general test. I don't have the technicians up yet. I've got all the PowerPoints done because we've been through it several times. I just haven't had the motivation to go through and to develop the videos because we haven't had anybody go through the technician study group for a while. So if you know somebody that's interested, let me know. So this is K3SKS 73, and I'm clear.